All right, I'm going to go over these notes to help you answer the questions in this assignment, which is your beam bending structural properties notes outline. Okay, so you have for these questions, blank is a mathematical property of a cross-section measured in inches to the fourth, gives us important information how that cross-sectional area is distributed about a blank axis, blank of an object related to its shape. In general, the higher moment of inertia gives a greater resistance to blank. Which of the above has a greater resistance to bending, and it has a blank to answer in. And then ask you to write the base and the height for these different beams in different orientation. This one's in what's called the vertical or joist position, and this is in the plank or the horizontal position. So you'll answer these questions as we're going along here, and I'll try to reference them as we're going. So first thing, in fact this is your first answer here, is moment of inertia. That's what you're filling in the blank from the previous slides. Moment of inertia is mathematical property of a cross-section measured in inches that gives important information about how that cross-sectional area is distributed about a centroidal axis. Okay, centroidal axis. You'll notice the key word here, centroid. We've been talking about the centroid as the center of mass for a shape. So this is the moment of inertia is a math calculation that will show us how the forces are aligned along the cross-sectional area distributed to that centroidal axis. Okay, it describes the stiffness of an object related to its shape. Okay, and in general, higher moment of inertia produces a greater resistance to, the word here is deformation. We would also call that bending. Okay, how resistant is the material to deformation or bending. So you have an example here of a diving board, and you probably either have been on a diving board or you've seen somebody bouncing. There's a lot of flexibility, a lot of bending that goes on with a diving board, unless of course you're on a diving platform like the one on the right. The one on the right here, this one is a diving platform which swimmers would use as a starting platform to dive into the water, and it has very little deformation or bending that happens. It's very stiff. Moment of inertia, principles. Okay, also I put the titles here for joist position, also called vertical. Okay, that's when a beam like this has a taller, okay, it's taller than its base. Okay, like that. Whereas the bottom one here is in the plank position, also called horizontal. You'll notice that its base is wider than its height. Okay, so both of these materials are made up of what's called Douglas fir. Okay, so the materials are listed here, Douglas fir. The length is the same, 8 feet, but again, as you notice here for beam A, the width of the base, okay, is 1.5 and the height is 5.5. Whereas beam B, the width is 5.5 and the height is 1.5, so they switch places. Okay, moment of inertia, you've got, again, these things are made up of the same materials, and the answer to this question, what distinguishes beam A from beam B? Okay, well, beam A and beam B are in different orientation. Beam A is in the joist position, and beam B, the lower one, is in the plank position. Okay, which one do you predict would bend more? Well, you may have an idea, maybe you don't have an idea. Okay, you should, in your own mind, just make a prediction. What do you think? Here it tells us that beam B will have greater deformation than beam A. The vertical, okay, the height is the most important factor in these two beams, in any beams, okay? If it's taller, it's going to have more resistance to deformation, okay? And so the difference between these two, the difference in the moments of inertia due to orientation, okay, has a different moment of inertia. So in other words, the resistance to deformation or bending is based on orientation. So orientation means, is it joist, okay, up and down like this, or is it plank, horizontal like this? That's what moment of inertia deals with. Our equation for moment of inertia is listed right here. I stands for moment of inertia, B is the base, H is the height. The height is cubed, and we divide by 12. So the height, you can see, is more important in this because it's cubed. It's the height cubed, not the base times the height cubed, but height cubed times the base. Okay, so when we calculate moment of inertia, for this example right here, we see the height is 5.5, the base is 1.5, and we do 5.5, and we want to cube that first before we multiply by 1.5 and divide by 12. So this is the math. You just punch these numbers into decimals. Again, make sure that you do 5.5 cubed first and then multiply by 1.5, divide by 12, and that will give you an answer of 21. That's the moment of inertia in the joist position. Okay, here's the moment of inertia for the same piece of lumber, but now in the plank position rather than the joist position. So now the height is 1.5 and the base is 5.5. So we're going to cube the height first, but in this example it's not 5.5, it's 1.5 cubed times 5.5 divided by 12. If we do that math in decimals, you're going to get an answer of 1.5. So when we compare them, in the joist position, the top one, the moment of inertia is 21. In the plank position, the bottom one, the moment of inertia is 1.5. So in the joist position, beam A is 14 times more stiff than beam B. These examples here are composite shapes. Okay, they're used in structural design because with a composite shape, we can get comparable results using a lot less material. So for example, we have a regular beam on the left here, and we have an I-beam. It's called an I-beam because, as you can see, it's shaped like the letter I. But it has quite a bit of the material that's taken out of it. If we were going to, use the beam on the left here, well, this is a horrible example, but you can see that all this material is taken out of the beam. Okay, probably not exactly like you're seeing that I'm doing it, but it ends up being like the letter I. Okay, that's left, and that's what you have on the right-hand side there. Okay, so what we have is, with the beam solid like it is, it has a moment of inertia of 10.67, and the I-beam on the right has a moment of inertia of 6.08. If we compare the area, the surface area of the beam on the left the area is 8 inches squared, with the area of the I-beam, the one on the right, is 2.7 inches squared. So what happens is the I-beam has 50, if we were compared the moment of inertia, the I-beam has 57% of the stiffness, okay? But it only uses 44% of the rectangular beam's material. So the I-beam, this one here on the right, okay, is not as strong as the one on the left. Okay, it's only 57% as strong. but it only uses 44% of the material. So you have a lot less waste of material, and you have to take the cost into consideration as well. If you can get an I-beam for less expensive than the regular beam, then you want to take that in consideration. And you may not need a moment of inertia to be 10.67. You may not need it to be that strong. So all those are factors you need to take in consideration. Now, the next part of this assignment is dealing with the modulus of elasticity. So on the assignment that we were working on, we're all the way to right here, material properties. Blank is the ratio of stress to strain. This is modulus of elasticity. It fits into this blank right there. Modulus of elasticity is the ratio of stress to strain. Okay, stretching, it's known as the coefficient of elasticity. It's also known as elasticity modulus and elastic modulus. Some people call it Young's modulus of elasticity. Okay. This defines the blank of an object related to the material chemical properties. In general, blank modulus of elasticity produces a greater resistance to blank. Okay, so let's take a look at our notes. This defines the stiffness, right there, of an object based on the material's chemical properties. In general, higher modulus of elasticity produces a greater resistance to deformation, also called bending or stretching, okay? Changing the shape of the material. Here now, instead of having the same material, when we're talking about modulus of elasticity, we're comparing different materials and their resistance to deformation. So in this case, we have a 2x6, which is ABS plastic. It's made of plastic, and the bottom one is a 2x6 made of Douglas fir wood. So what distinguishes them? What distinguishes them is what they're made of. Okay, and because they're made of different materials, they're going to have a different modulus of elasticity number. And those numbers are already calculated. There are charts that contain the modulus of elasticity for both of them, or they would be given to you in a problem. Okay? So, question, will beam A or beam B have a greater resistance to bending if an identical load is placed on both beams? We're going to do some problems that we place a load of 250 pounds onto the beams. Okay. Why did beam B have a greater deformation than beam A? Okay, so it's telling us that the top one has a greater deformation than the bottom one. It's going to bend a lot more. The plastic will bend more than the wood. Okay, so it tells us the answer. Why did it have a greater deformation? Because the plastic is weaker. It has a smaller modulus of elasticity. Okay, so the modulus of elasticity number is going to be smaller, means it bends more. Deflection is the amount an object is displaced under a load. And the characteristics, these are the 4 characteristics that you're going to answer your questions that affect the deflection. And deflection has a symbol of delta max. Okay, this triangle maximum. So it means delta max means how much will it bend. The 4 factors that determine the maximum deflection are the force, also called the load, the length of the span, and that needs to be in inches, the modulus of elasticity, and the moment of inertia, what we were just talking about previously. Those are the 4 things. When we compare ABS plastic to Douglas fir wood, okay, if everything else is the same, in other words, the length, let's change this color so you can actually see it a little bit better. The material is different. We have fir, Douglas fir compared to plastic, but the length is the same, 8 feet and 8 feet. The width is the same, 1.5, 1.5. The height is the same, 5.5, 5.5. The area is the same, 8 1/4 and 8 1/4. The moment of inertia is the same, 20.8, 20.8. Okay? When we calculate the maximum beam deflection, force times the length cubed, that's in length in inches, divided by 48 times Young's modulus times the moment of inertia. Again, everything is the same except for this right here. Everything else is exactly the same. So the modulus of elasticity is dealing with the difference in what these two pieces of material are made of. One of them is made of plastic and one of them is made of wood. The wood has a modulus of elasticity of 1.8 million. PSI stands for pounds per square inch. The plastic is 419,000 PSI. When we calculate this, we put the numbers into this equation and we get force times the length cubed. And again, the length needs to be in inches. So you'll notice taking the numbers off of this chart right here and putting them into this equation, we get the length is 96 inches. Remember, it was 8 feet up here, right here, 8 feet, okay? 8 times 12 inches per foot gives us a number of 96. And we're going to cube that. 96 cubed times the force, 250 foot-pounds, divided by 48 times 1,800,000 PSI times the moment of inertia, 20.8 inches to the fourth. And that gives us a maximum deflection of 0.12 inches. When we compare that, putting the numbers into this formula again, but now using the plastic, okay, instead of the wood, okay, everything's the same. 96 inches cubed times 250 divided by 48 times, in this case we have 419,000 PSI. Okay, that number comes from right up here. Okay, right there. That's the Young's modulus of elasticity for the plastic. And the moment of inertia is the same. We get a maximum deflection of 0.53. Okay, so when we compare these, we get the maximum deflection for the wood was 0.12 inches. So it's a little less than 1/8 of an inch. For the plastic, the maximum deflection was 0.53. It's about 1/2 an inch. So the plastic will bend further than the wood. Okay, so this would be the plastic. You can see it's bending further than the wood, which has a little bit of a bend to it. And that's understanding moment of inertia and modulus of elasticity, maximum deflection. Email me if you have any questions.